the first thing that happened that year was that we were about to start a new center of excellence. It was a first generation Norwegian center of excellence called PGP, Physics of Geological Processes. And then we hired Hans Amundsen to be responsible for outreach and media. And it turned out that Hans had some friends who was interested in this mysterious branch of science called astrobiology. There were people from NASA and Carnegie and other places. And they wanted to go to Svalbard, to use Svalbard as a field analog for testing out equipment, looking at life on Mars and possibly other planets. So Hans suggested to us that we should sponsor this expedition, the Arctic Mars Analog Svalbard Expedition, AMAZE, promising that this would give us a lot of media attention, and this was absolutely true. We were all over media very shortly after we started this. And he took us on to Woodfjorden, which is up here, as previous speakers have shown you. This is Woodfjorden, and the Woodfjorden is this little branch of the Woodfjorden. And so this is the fjord here. And along Woodfjorden, there is this fault separating the Devonian sedimentary rocks from the basement. And along this fault, there is this blue little dots, which are 2 hot springs. And to my knowledge, it's the northernmost hot springs on land. It's the Jotun spring in the north and the Troll spring in the south. And if you stand on the Troll spring looking east towards the Devonian basement on a nice day in 2003 in August, it looks like this. This is where the hot water is coming up. It's not terribly hot. It's 25 degrees approximately. And these are the Devonian rocks, which looks better a bit later in the day when the sun is in west. A spectacular, typical sandstone colored by the sun. If we continue walking along Woodfjorden towards the south, or you fly in helicopter, you will see the Troll springs emerging. They're more spectacular in terms of carbonate precipitated around the spring. Here is the spring, it's flowing downhill, precipitating carbonates. You have the large-scale structures, and there are these small terracets, they're called. So there are different kind of terraces at different scales here. We also, from the helicopter, Oh, okay. Yes, so this is another image from the helicopter, and we also took this image here with infrared so we could see, whoops, show up here. Okay. That part was a very nice infrared image showing you the temperature field, and the source is obviously hotter than the rest. But we do have the temperature here too. We had temperature loggers in the one in the air and one in the spring source, and one is more distant downhill in the spring, measuring temperature for approximately 1 year, showing you that in the air the temperature reached a maximum of 10 or 15 or so during the summer, and then it's colder in the winter. It doesn't get terribly cold, minus 15 perhaps. It's not as noisy when it's covered by snow. It's dampened by the snow cover here. Whereas in the spring source, the temperature varies from about 25 in the summer. It's cooled down a bit in the winter. Sometimes it's close to freezing, so it must be reflecting variable flux of water coming up from the hole. And when it's a low flux, it gets colder. This is what the travertine, and we call it travertine, the carbonate terraces, looks like if you cut it in with a saw. And it's clearly a very layered. The yellowish layers are probably a bit more iron-rich than the other layers. The picture to the right here is with the ultraviolet light. But the actual growth is normal to the surface. It's made up by these fibers of carbonate. If you look closely at the fibers, sometimes you can see small striations separated by just a few microns, and we think that is diurnal variation in the growth. So if we assume that this is the case, we could estimate the growth rate, and it would be typically on the order of 4 or so millimeters per year. So it's a very slow growth, but the growth rate will depend on where you are in the pool, of course. If we do cross-section of oxygen and carbon isotopes, we see we have peaks separated by about 10 or so millimeters, and we assume this was the result of annual variations in temperature. So in this particular case, for this sample, the growth rate would be on the order of 10 millimeters or a centimeter per year. So that's relatively slow growth for a travertine deposit. We wrote a paper with Eivind Hammer. So Eivind Hammer is working at the Natural History Museum, and he was part of this first expedition, and we did quite a lot of work later on with Eivind and also Dag Dyste, physicist at the University of Oslo. This is a picture of the pool. The source here is flowing downhill. The oxygen and hydrogen composition of the spring water is close to the meteoric waterline, and evolves a bit when it's degassing down the slope. But note that the composition is at much lower values of hydrogen and oxygen compared to, for example, a current cold spring or the average glacial composition in a period from 1920 to 97. So the lower these values are, the colder is the climate usually assumed to be. So these meteoric waters, which come up in the spring, is probably has been formed as meteoric water when the climate was colder. Also, this spring water is quite rich in helium, and this high helium content, if it's not from the mantle, and the isotope data suggests it's actually meteoric, suggests that the water has a long residence time in the crust. These are contoured diagrams showing here again the spring, elevation, so low elevation, high elevation, the temperature field here, the temperature cools down from 25 and to 10 or 15, whatever the ambient temperature is. pH is low when the water gets out of the spring, is 6.5 or something. Then degassing of CO2 downhill increases the pH. You lose an acid and you increase the pH, so it's basic solutions. And this transition from more acidic to basic solutions is actually what drives the precipitation of carbonate in the terrace system. So CO2 is going down, getting darker, these lower values, and the calcium content of the fluid is going down. So after having characterized the fluid, written papers about the fluid composition, but general geochemistry just to describe it. And the next question was, what is the mechanism behind the formation of this terrace landscape on different scales? So this was what most of us from PGP did. Hans was interested in looking for life on Mars and testing equipment, etc. Most of us were not astrobiologists, but we were interested in the sort of dynamics behind pattern formation in general on the Earth. And in this case, we saw this fascinating pattern formed by the combination of precipitation and flow. So how could these patterns emerge? And these patterns are actually quite common and very spectacular. This is from Turkey, very large scale structures. The exact details depends a bit on the slope. So the slope is very important for these patterns to form. This is from Yellowstone. It's a Grand Prismatic Spring. This is really boiling water. And you see similar terraces, but these terraces are not carbonates, it's silica. So you see very similar morphological terrace landscapes in many different systems. We have a combination of flow of fluid and precipitation. You even see it on ice. If you look at a little creek when it's freezing, it's not a smooth surface, it's a terraced shape. Even if you precipitate particles from a flowing fluid, like pine needles here, you have a tendency to form little terraces rather than a generally smooth surface. So why is that? And you see it on icicles as well. These are icicles. These are carbonate stalactites. They have a very similar shape. Quantitatively, it's the same kind of shape. And what if carbonate is precipitating from a fluid that is not really flowing? And then you don't break the symmetry. You just get these bumpy structures. It has a name. What's called again? Now I forgot it. Botryoidal, which means like a bunch of grapes. And it actually looks maybe more like cauliflower or broccoli than actually grapes. It has this roundish shapes with bumps on it. We see it also on moss, for example. So this is also a shape that is very common in inorganic systems and in organic systems. And also the microstructure, if you cut through this moss, you will see these fibers that are branching towards the surface. The general growth is towards the surface, so it's surface normal growth. But because the sphere that is growing becomes bigger and bigger, you need to branch the fibers basically to cover the surface. So this is the moss to the right, and these are one of the carbonates from Svalbard to the left. It's quite a common, they have many common features. Again, a natural carbonate surface. And because surface normal growth generates spheres, you can fit these surfaces to a bunch of spheres very accurately. If you add a little bit of noise to this fit, you can hardly distinguish the fitted surface to the natural surface. So if you nucleate carbonate, you let it grow normal to the surface, it will make a sphere. If you nucleate it on a flat surface, it will make a half sphere. Each time there will be a new nucleation event, you grow a new sphere. So you get an assembly of big and small spheres. The small ones form later or nucleated later than the big ones. So that's, although this surfaces look very complex, you may think it's all sort of complicated physics and chemistry behind it. It's just nucleation, surface normal growth, and then you have nucleation repeated through the history of the formation of the structure. And then you add a little bit of noise on top of it. Microstructures look like this. These are fibers growing normal to the surface. You need branching to cover an increasing surface. And when two of these structures meet, there will be a depression at the surface in between. It's just like you see it in the carbonates this is actually from Sverige, from one of the pipes, gas chimneys, which also precipitated carbonates. Now, what happens if you add flow to the precipitation? Then if you then eject water on the surface and tell the water that you precipitate faster where you're close to where you exit, which is reasonable because when the fluid is moving away from the source, you have degassing and there is less of the dissolved species in the solution, so you decrease the growth rate and let it grow for a while. Then you see that you can get a very nice fit to this structure, which is in Mammoth, also just north of Yellowstone, with a very simple growth rate formula where the growth rate is only a function of the distance S from the outlet and a fit factor. So if you flow a fluid down a slope with a little bumpy surface, a little bit of noise on it, and just tell the fluid that you will precipitate something on the surface and the precipitation rate will be higher where the flow rate is highest. You will see that the structure evolves and it forms a pattern. There is a movie fitted to this that I didn't have time to find on an old computer, but I'll show you how it evolves here. The upper left is a very noisy initial surface, telling the fluid that flows down the slope here that it will precipitate faster where the flow rate is high because the slope is high. It will develop into travertine-looking structures. So again, very simple precipitation, but the precipitation rate that depends on the local flow rate. Also, the terrace landscape will coarsen because small terraces will drown in the big ones. So you will end up with big and few terraces from something that was fine-grained in the beginning. So then the question is, why does precipitation happen faster when the slope is high or the flow rate is high? So we did an experiment to figure out that. This is a flow channel where flow is from left to right. Again, I don't have the movie, but we have placed an obstacle here. So the fluid will have to flow above the obstacle. And then the fluid film will thin. And when the fluid film is thinner, the flow rate will be higher. But also when you have a thick fluid film and you make it thinner, then the concentration gradients within that film will be increased. You have the same difference between top and bottom, but the distance is much shorter. When the concentration gradients are higher, the diffusion out of the system of gas, for example, CO2, will increase. So even laminar flow, just because you thin the fluid film and diffusion becomes more efficient, you will lose more CO2 and you will have a higher supersaturation where the flow rate is higher. If it's flowing fast, you will get turbulence, which is another way of losing CO2 in this system. So we did this experiment, calculated precipitation rate. Now this is actually the measured precipitation rate around an obstacle here. And these are the fitted to a model where we actually calculate the concentration as a function of the flow rate for different parameters. And the bottom parameter is corresponding to the experiment we did. So we see we have a pretty good fit between what we measure in terms of precipitation and what we actually predict. So we felt that we really have understood the formation of terrace landscapes in carbonate systems and in other systems with this simple coupling between flow rate and precipitation rate. So after this, me and Eivind wrote this book, Sculpting of Rocks by Reactive Fluids, which was a totally curiosity-driven project. There was no thought of relevance for anybody. It was just, how on earth do these pattern landscapes form? Of course, then, if you start understanding this coupling of flow and precipitation and pattern formation, it has some relevance in some systems. For example, we started to look at growth in pipelines. Scaling is a well-known problem in the petroleum industry. For example, if the pipelines clog because of precipitation, this is a big issue. And of course, in Iceland, there are lots of pipelines and very hot fluids, and they precipitate stuff inside the pipelines. And what's precipitating is silica, amorphous silica. It ends up like this. And this has a big effect on the flux of fluid in a pipeline. If you look at the equation for flow or flux through a pipeline, normally the flux is given by the diameter and the radius of the pipeline and the driving force. But if you precipitate a thin layer of this very rough material on the walls, it actually has a big effect on the flow rate, because you get an effective friction. When fluid is passing over this, you will get all sorts of small little eddies, and these will lose energy. You will dissipate heat basically near the walls, and this will slow down the flow rate much more than I expected. Icelandic people told me that if you get this on the walls, it actually makes a difference, although it doesn't make a big difference to the overall radius of the pipeline. So to understand the formation of these silica structures, we stuck some steel plates into the pipelines. There's a guy who helped us with that. And then we looked at the precipitate after a period of time inside the pipeline. And what's precipitating here is looks like sitting butterflies of amorphous silica. Here's an individual guy here. Clearly asymmetric. It's pointing in one direction. And I had a PhD student who was funded by an EU project on scaling, Christopher Hawkin, and he made his movies. This is flow from left to right. We nucleate this precipitate. It's growing towards where the fluid is coming. And when you nucleate many, the evolution of them will depend on the flow close to the surface, because this little dew dust, Trond would call it, that grows out will generate a little eddy, a bit of turbulence behind them. So there is a natural pattern evolving in this system. And if you start looking at some of these, the shape will depend on the Peclet number. So that's says something about the relative rate of diffusion compared to advection, and the Rayleigh number. You see that some of these are quite similar to these butterfly-like structures we actually observe in the pipelines. So these studies that started at Svalbard on coupled dissolution precipitation at the Troll Spring actually made sense when we got to this. We had the relevance as an additional thing. And when you start to look more into growth, you can also study growth in confinement, for example, what happens when things are growing in pores. Of course, there can also be flow rate through a porous medium, and things like salt or other materials will grow in the pores. And when the fluid is sufficiently supersaturated, the growth will generate a force on the material. And this is why you, for example, generate structures like this. This is from a graveyard in Whitby in Yorkshire in England on the east coast. Captain Williams died at some stage, 17 or 1800 and something. And this sandstone has been developing the pattern because probably a lot of seawater with salt is splashing onto the grave, and salt is growing in the pores of the sandstone, and grains of sand will fall out, and the structure is quite spectacular. This is another pattern formation from a trip we had to Argentina with Sverre and Olivier and others, where this andesitic intrusion, it's quite porous and it reacts with the meteoric groundwater, and the precipitation causes a force inside the rock, so it cracks, and when it cracks open, more fluid gets in, and this process generates this quite fascinating pattern inside what used to be a homogeneous andesite, just by weathering and growth in the pores. And what's growing here is ferrihydrite, mainly. It's a hydrous iron hydroxide. Okay, I think I'll leave it there. It's so you see, this was, we just went somewhere to look at whatever was there, and it had all sorts of offsprings, and this has happened a couple of times in my career. With Sverre, we went to Karoo in Africa to look at pipes through sandstones there too, and figure out, or Henrik Svensson and collaborators figure out that this actually may have implications for global